Hi, in this lecture, we're going to examine the deep ocean basins as dynamic environments shaped by heat flow, chemical exchange, and biological processes. Rather than focusing on the shape of the seafloor or the motion of the plates, our goal today is to understand what kind of physical and chemical conditions exist within the deep ocean basins and how those conditions support life and long-term sediment accumulation. Deep ocean basins are cold, dark, high-pressure environments, but they are not inactive. Heat continues to escape from Earth's interior through the ocean floor, seawater circulates through the crust, and unique ecosystems thrive far from the sunlight. Understanding these processes is essential for understanding how the deep ocean functions as part of the Earth system. A deep ocean basin refers to the broad, deep regions of the ocean floor that lie beyond continental margins and are underlain by oceanic crust. These basins are not defined by a single landform, but by their depth, their age, and their thermal state. Because oceanic crust cools and subsides over time, deep ocean basins represent the most thermally evolved parts of the ocean floor. They are far from continental influence. They are physically stable, and they're shaped by processes that operate over millions of years. These characteristics make them ideal environments for studying heat flow, chemical exchange, and long-term Earth history. This image shows the deep ocean basin of the western North Atlantic Ocean off the United States East Coast. The basin is shown in the dark blue. The basin also includes the Mid-Atlantic Ridge, but it does not include the continental shelf, slope, or rise. As a brief review, remember the oceanic lithosphere forms hot at mid-ocean ridges and cools as it moves away from those ridges. Cooling causes the lithosphere to contract, which then increases the density and causes it to sink. This thermal evolution explains why deep ocean basins exist and why they deepen with distance from ridges. This cooling process also controls how heat escapes from Earth's interior and sets the stage for hydrothermal circulation within the crust. Deep ocean basins are defined by a set of extreme physical conditions that differ fundamentally from those at the ocean's surface. The first of these is depth. In most deep ocean basins, the seafloor lies 4 to 5 kilometers below sea level, and in some areas even deeper. As depth increases, pressure increases because of the weight of the water above it. In the ocean, pressure increases by approximately 1 atmosphere for every 10 meters of depth. This means that organisms living at 4,000 meters depth experience pressures hundreds of times greater than atmospheric pressure at the surface. This high pressure affects everything from the structure of biological membranes to the behavior of gases and chemical reactions. Temperature is another defining feature of the deep ocean. Below the surface layers, temperatures drop rapidly and then remain uniformly cold, typically just a few degrees above freezing. Unlike surface waters, deep ocean temperatures are remarkably stable over time, showing very little seasonal or daily variation. And finally, sunlight does not penetrate to these depths. The absence of light means that photosynthesis cannot occur, fundamentally altering how energy enters deep ocean ecosystems. Let's pause here for one moment so we can think carefully about the consequences of no sunlight and no photosynthesis. What do you know about food webs and the foundation of all food in that web? Almost all food webs are built on a foundation of photosynthetic organisms. So how is it possible for life to exist in the deep sea where there is no photosynthesis? Write down your ideas here, and let's see if we can answer this question later in the lecture. Together, high pressure, cold temperatures, and permanent darkness create an environment that strongly constrains physical, chemical, and biological processes in deep ocean basins. Although the deep ocean is cold at the surface, deep ocean basins remain thermally active. Heat continues to escape from Earth's interior through oceanic crust. Heat flow is highest near young crust and decreases as the crust ages, but even the oldest parts of the ocean basin continue to lose heat. This heat flow is a fundamental driver of chemical exchange between the ocean and the crust, and is the reason hydrothermal systems exist in the first place. So let's spend some time exploring heat flow through the ocean floor. It is quite interesting. Heat moves through the oceanic crust in two fundamentally different ways: conduction and hydrothermal circulation. And the difference between these processes is critical for understanding chemical reactions in deep ocean basins. Conduction is the slow transfer of heat through solid rock. Thermal energy moves from hotter regions of the crust to cooler regions without the rock itself moving. This process operates everywhere in the oceanic lithosphere, but it is relatively inefficient. Conduction alone cannot remove heat fast enough to explain the observed heat loss from ocean basins. The much more important process is hydrothermal circulation, sometimes referred to as fluid circulation. As you can see on the image on the right, seawater penetrates cracks, fractures, and pore spaces in the oceanic crust. As this water moves downward, it is heated by surrounding rock and begins to react chemically with the minerals it encounters. The heated water becomes less dense and rises back toward the sea floor, carrying heat and dissolved chemicals with it. As seawater circulates through the crust, a number of chemical reactions occur. For example, magnesium is removed from seawater as it reacts with basaltic minerals, while calcium and other elements are released into solution. Sulfate in seawater can be reduced, and metals such as iron, copper, and zinc can be mobilized. These reactions fundamentally change both the composition of the circulating fluid and the oceanic crust itself. This combination of heat transfer and chemical reaction means that hydrothermal circulation is not just a physical process. It is a major mechanism by which the ocean and solid earth exchange materials. The altered fluids that return to the ocean play a key role in shaping seawater chemistry and provide the chemical energy that supports hydrothermal vent ecosystems, which we will examine in the next several slides. Hydrothermal systems vary widely in temperature, chemistry, and geological setting. Some systems involve extremely hot fluids emerging in focused jets, while others release warm fluids over broad areas on the seafloor. In addition, some hydrothermal systems form through reactions between seawater and mantle-derived rocks, producing chemically distinct alkaline fluids. Despite these differences, all hydrothermal systems share the same fundamental mechanism: seawater circulating through hot oceanic crust. High-temperature hydrothermal vents, commonly referred to as black smokers, represent the most extreme end of hydrothermal systems found in deep ocean basins. These vents typically occur near mid-ocean ridges where oceanic crust is thin and heat from underlying magma is relatively close to the sea floor. In these systems, cold seawater penetrates deep into the crust through fractures and faults. As the water descends, it approaches very hot rock, sometimes only a few kilometers above molten magma. At these depths, the water can be heated to temperatures exceeding 350 degrees Celsius. Yet it does not boil because of the immense pressure at depth. As the fluid heats up, it reacts chemically with the surrounding basaltic rock. Metals such as iron, copper, and zinc are leached out of the crust and carried upward in solution. The fluid also becomes acidic and chemically reduced. When this superheated, metal-rich fluid is expelled back into the ocean and mixes with the cold seawater, the dissolved metals rapidly precipitate as sulfide minerals. This precipitation creates the dark, smoke-like plumes and chimney structures that gives black smokers their name. From a basin scale perspective, black smokers represent highly focused points of heat and chemical transfer. Although they occupy small areas of the seafloor, they play an outsized role in removing heat from Earth's interior and in supplying chemically reduced compounds that support unique biological communities. Before moving on, let's pause here so you can take a close look at the black smoker GIF that is on the slide. Look carefully as it transitions between images, and you will see shrimp and crabs living at these vents. Even with this extreme pressure and the super high temperatures and the lack of sunlight in these very deep places, we're finding thriving ecosystems full of life. How amazing is that? While black smokers are visually dramatic, they represent only a small fraction of hydrothermal activity in deep ocean basins. In fact, most hydrothermal circulation occurs through low temperature, diffuse flow systems that are far less conspicuous but equally important. In diffuse flow systems, seawater still circulates through fractured oceanic crust, but it does not approach magma bodies closely enough to reach extreme temperatures. Instead, the circulating fluids are warmed to relatively moderate temperatures, often only tens of degrees above the surrounding seawater. These fluids then seep slowly and broadly out of the seafloor rather than erupting in focused jets. Because diffuse flow occurs over much larger areas than black smokers, it accounts for a substantial portion of the total heat lost from oceanic crust. Chemically, these systems still alter seawater composition, though the changes are more subtle. Elements may be exchanged between rock and water, and reduced compounds can still be supplied to the ocean, but at lower concentrations. From an ecological standpoint, diffuse flow environments often host extensive microbial communities and serve as important transitional zones between high temperature vents and the surrounding deep ocean. Recent research has discovered a community of viruses that infect bacteria cells along these vents. The viruses take globules of elemental sulfur stored inside the bacteria cells and then somehow convert that sulfur to energy that is used to propagate themselves. At the basin scale, diffuse hydrothermal circulation represents a continuous, widespread mechanism by which heat and chemicals are transferred from Earth's interior into the ocean. And clearly, the process is having a direct impact on the biological community that lives there. This is another reminder that there is so much more to discover on the ocean floor. Alkaline hydrothermal systems represent a chemically distinct type of hydrothermal activity and occur in geological settings different from typical ridge-axis vents. Rather than forming primarily through interaction with basaltic crust near magma, these systems develop where seawater reacts with mantle-derived ultramafic rocks. This is a process known as serpentinization. During serpentinization, water reacts with minerals in mantle rocks, producing heat and generating fluids that are rich in hydrogen and highly alkaline. These fluids tend to be cooler than black smoker fluids, often in the range of tens to low hundreds of degrees Celsius, and they can persist for very long periods because they do not require an active magma source. The chemical conditions created by alkaline hydrothermal systems are especially important. High concentrations of hydrogen and strong chemical gradients provide abundant energy for chemosynthetic microorganisms. Because these systems can be stable over long time scales, they are of great interest for understanding sustained deep-sea ecosystems and have been proposed as possible environments where life may have originated on Earth. As seen on the left image, pores in the vents have a similar topology to that of single-celled autotrophic cells. Both have a membrane-like structure that maintains a proton gradient and a pH difference between the inside of the membrane and that of the surrounding water. In the context of deep ocean basins, alkaline hydrothermal systems highlight the diversity of ways that heat and chemistry can be transferred from Earth's interior to the ocean. They reinforce the idea that hydrothermal activity is not limited to a single setting or a temperature range, but it is a widespread and varied feature of the oceanic crust. Up to this point, most of the life on Earth you have learned about in other classes are either explicitly or implicitly tied to sunlight. At the surface, sunlight drives photosynthesis, which forms the base of most food webs on Earth. In the deep ocean, however, sunlight is completely absent, and yet life persists. This is possible because of a fundamentally different biological process known as chemosynthesis. Chemosynthesis is a process in which microorganisms use chemical energy rather than light energy to produce organic matter. In hydrothermal vent environments, this chemical energy comes from reduced compounds such as hydrogen sulfide, hydrogen gas, or methane that are released during hydrothermal circulation. Microbes oxidize these compounds and use the energy released to fix carbon into organic molecules. These chemosynthetic microorganisms form the foundation of deep sea vent ecosystems. They occupy a role similar to that of plants and phytoplankton in sunlit environments. Instead of capturing energy from the sun, they capture energy from chemical reactions fueled by Earth's internal heat. This process is important not only because it supports life in the deep ocean, but also because it fundamentally changes how we think about where life can exist. Chemosynthesis demonstrates that biological systems can be directly linked to geological and chemical processes occurring within the Earth rather than relying on surface conditions. The deep sea benthos includes all organisms that live on or near the seafloor in deep ocean basins. These organisms inhabit environments characterized by extreme pressure, cold temperatures, and limited food availability. As a result, many deep sea organisms grow slowly, reproduce infrequently, and have long lifespans compared to organisms in shallow waters. Away from hydrothermal vents, most benthic organisms depend on organic matter that sinks from the surface ocean. This material arrives slowly and in small amounts, making the deep ocean a generally low-energy environment. Biological communities in these regions are often sparse and widely spaced, reflecting the limited availability of food. Hydrothermal vents, however, create localized biological hotspots within this otherwise food-poor environment. Vent communities are densely populated and highly productive because they are supported by chemosynthetic microbes rather than sinking organic material. Many vent organisms, such as tube worms and clams, host chemosynthetic bacteria within their tissues through symbiotic relationships, allowing them to tap directly into chemical energy supplied by vent fluids. The distribution of deep sea life is therefore strongly controlled by geology. Where hydrothermal circulation delivers heat and reduced chemicals to the sea floor, biological communities can flourish. Where it does not, life persists at much lower densities. This close coupling between geological processes and biological patterns is a defining feature of the deep ocean basins. I hope our discussion so far has demonstrated the deep ocean basin is not just a flat, static floor, but instead is a very dynamic bottom that interchanges constantly with Earth's inner core. Although hundreds of hydrothermal vents have been discovered, I do not want to leave the impression that the deep ocean basin is covered with hydrothermal vents. In fact, the vast majority of the deep ocean basin consists of an extensive flat bottom with thick layers of fine sediment. In fact, the sediment can be so thick as to completely cover seamounts and other topographical features. The vastness of the deep ocean basin has allowed for long-term accumulation of sediment. Because deep ocean basins experience little erosion and relatively weak physical disturbance, sediments that reach the basin floor are often preserved rather than reworked. Over thousands to millions of years, particles derived from the continents, the surface ocean, hydrothermal systems, and biological activity settle and become layered on the sea floor. Each layer records information about the conditions under which it formed. The deep ocean basin therefore functions as a natural archive, integrating signals from Earth's climate system, ocean circulation, biological productivity, and geological processes. The same thermal stability, chemical environment, and biological constraints that define life in the deep ocean also control how sediments accumulate and what information they preserve. In this lecture, we have focused on deep ocean basins as physically stable, thermally active environments shaped by heat flow, chemical exchange, and unique biological processes. These same conditions also make deep ocean basins ideal places for sediment to accumulate over long periods of time. In the next lecture, we will shift our focus to marine sediments, examining what types of materials settle in the deep ocean floor, where those sediments come from, and how they accumulate so slowly and continuously. We will also explore why deep sea sediments are such powerful records of Earth's climate, ocean circulation, and biological history. Understanding the deep ocean basin as a physical, chemical, and biological environment is essential for understanding the sedimentary record it contains.